So welcome to the session. We're going to talk about tree-based machine learning methods. And what I would like to say before we start is that the material in this session, in today's session, will be based on the following sources. So first of all, there is a chapter in the book, An Introduction to Statistical Learning with Applications in R. There's a chapter in this book that covers tree-based machine learning. So that's very interesting for you to read as background material. And then in particular, I'm gonna apply these tree-based machine learning methods to insurance data. So I will take a focus of modeling frequencies, severities data. And that has certain implications in terms of the choices and the approach that you will take. And in that respect, I warmly recommend you our very recent paper entitled Boosting Insights in Insurance Tariff Plans with Tree-Based Machine Learning Methods, it should be. That's a paper written by Roel Henkaerts, Marie-Pierre Coté from the University of Laval, myself, and Roel Verbelen from Affinity Consulting in Sydney. So that's going to be a very important resource and background reading for today's session and for the next session, in which we will dive a bit more into interpretability tools and the practical implementation of these tree-based learners, right? The visuals that I will use in today's deck of sheets are again taken from the website Machine Learning for Everyone in Simple Words with real-world examples. Yes, again. Okay. So that is in terms of the copyright acknowledgements. So what are we going to do today? Well, we're going to dive a bit into this field of machine learning, right? And I thought it was nice to start with this visual where you see, okay, you've got the bigger field of artificial intelligence of which machine learning is part. And then within this machine learning world, you could also explore the use of neural networks, deep learning method. That's not what we're going to do at this point. So here we're going to dive into specific methods, let's say, from the machine learning world. Now, everything that has to do with tree-based learners, right? And we've seen this picture or this roadmap, we've seen it in the week before the Easter break. So if you look at these different types of machine learning methods, we already discussed last time that you can look at classical machine learning techniques, think generalized linear models, think generalized additive models, think a decision tree, so that's, or a regression tree, that's what we will cover today. So this is particularly interesting if you have rather simple data structures with features that are clearly defined, that are very nice, cleaned up, etc. And what we're also going to do today is dive a bit into this world of ensemble methods. So then we're going to take a basic classic machine learning technique, in this case, a simple decision tree or a regression tree, and create ensembles of such weak learners, put them together in order to create a more powerful learning technique, right? So that's important to keep in mind for today, that we're a bit exploring this part of the map that you see over here, and then also the part of the ensemble methods which belong to this particular area in my roadmap. Okay. So today's mission is twofold. I want to give you a quite broad and general discussion of what is a decision tree, what is bagging, what is a random forest, what is a gradient boosting machine. So that's essentially what we're going to do today. And here and there, I will make the switch to specific considerations that one has to keep in mind if one wants to use these predictive modeling techniques with a view or with the goal of modeling frequency severity data. Yeah? So here and there, we're gonna go from traditional textbook description of what is a decision tree, what is a random forest, what is a GBM. We're gonna switch to what are the implications if you wanna use these methodologies on insurance data, right? So that's the goal for today, to give you this broad discussion so that at the end of the session, we know what these different methods, how they work, what the tuning parameters are, what the general principles are, and so on. And then in the next session, I will cover coding illustrations, and I will work particularly on designing useful interpretation tools, so that you can sort of look under the hood of such a gradient boosting machine, for instance, and get an understanding of which features are important, how is the response changing as a function of a certain feature, what kind of interactions are picked up, and so on and so forth. Yeah? So that will be for one of the next sessions. Okay. So we've got 4 methods on the agenda. So the first is a decision tree or a regression tree. Then we're going to talk about bagging. Then we're going to talk about random forests. And then we're going to talk about boosting, right? So this first method, the decision tree, is going to take most of the time. Why? Because it's an essential building block also for the other methods. And for each of the methods, I will try to give you a visual taken from this brilliant website that I mentioned at the beginning of the class. So here we see, if we look at a tree, and in this case, it's a decision tree, what are the working principles of such a tree? Well, in fact, this is a very easy to understand scheme. It's kind of a flow chart. It's kind of a, yeah, it's a decision tree. So you, in this case, you want to answer the question, should I give a loan? Credit to a particular client of my bank, let's say. And then I'm going to verify a couple of things, like what is your credit history? Is your credit history good? It's an American example. Do you have a debt that is below, let's say, $1,000? Then yes, we'll grant you the credit. If no, we're not going to grant you the credit. So if you move through this tree for a new client that is entering the bank, and if you have certain features of this client available, then you can work through this tree, and in the end you'll see, okay, the answer to my initial question is yes or no. So we call this a decision tree because we're modeling here a response variable, a target variable, that in this case can take 2 labels, yes or no, right? If we're gonna apply this same reasoning to a regression question, where we're trying to model, let's say, a numeric outcome or a discrete outcome, then we're going to call it a regression tree, and we're going to use essentially the same kind of structure, but in a slightly different way, of course. Yeah? So that's what I want to discuss right now. Good. So what is a decision tree? What is a regression tree? So I will use the names as synonyms, but keep in mind you typically call it a decision tree if you're modeling a target variable that can only take a few levels, typically 0, 1, yes or no. You talk about a regression tree if you're modeling a numeric outcome, like in a regression setting, or if you're modeling a frequency outcome, like in the case of insurance frequency modeling, and so on and so forth, right? So let's start with simple examples and then generalize this to the context of insurance modeling. So the basic algorithm that was designed in the 80s by Leo Greiman and co-authors for handling, for working with these type of trees is called the CART model. It stands for classification and regression trees. So classification or decision tree, and then here you see the analog for a numeric outcome, and that's my regression tree. So if I look at an example of a regression tree, I'm going to start with the example given in the book on an introduction to statistical learning. So what they're doing here is they're using a data set called the Hitters data set in R to predict the salary of a baseball player, right? In this case, it's the log salary. So the numbers that you see as the outcomes are on the log scale. And you have a certain number of features available about these baseball players. Now, I don't know anything about baseball, but apparently what matters here in this prediction model is the number of years you've been playing in the league and the number of hits you make per season or something, or per game, or I don't know what, right? So how does this regression tree, how does that work in this particular example? So in this case, there are two questions that we should ask ourselves. Are you playing in the years for less than 4.5 years? If so, then we're going to predict your log salary with the value 5.11. If not, then we're asking an additional question. Is your number of hits below 117.5? Yes or no? And then we here have the predictions that we deliver for these players. So this, if we take the hitters data set, this is apparently the final tree that we come up with after a careful tuning process of our regression tree model. So what we're going to do now is we're going to go through this process. So how was this tree constructed? How should you understand the working principles and so on and so forth, right? But what you should get out of this picture is, once again, if a new baseball player comes to you and you want to make a prediction for his salary, then you need to know information on this covariate years, you need the information on the covariate hits, and then you can use this flow chart to come up with a prediction. Yeah? So the question here is, why do we use these two features, years and hits, and not any other features? And why do we make the split, particularly for the values that you see listed over here? We say that this is a tree with depth 2, because we take 2 of these questions, and the number of leaf nodes is 3, right? So because we have a leaf node here, 1 over here, and 1 over here. We call it a tree, but of course you should sort of picture it upside down, because the leaf nodes here are printed at the bottom, whereas in a real tree that would be the other way around. Okay, so thinking of what does this tree do with my feature space? Well, I can look at the following picture, where I take the space that is spent by the 2 features which matter in the tree that I showed on the previous sheet. And in this case, that's the covariate years and the covariate hits. So this is fairly simple. I only have 2 covariates. I can make their scatter plot. And what I see here with these orange dots is these are my baseball players in the training set that I used to develop, to build this tree, right? So each orange dot is representing a baseball player and is using the number of years that he played in the league and the hits that come with this baseball player. And what do we do then? Well, we see that the tree is splitting this feature space into rectangles, which are non-overlapping, which are distinct, and which altogether form this, this feature space, right? And we also see that the way how these rectangles are constructed, that corresponds to the questions that the tree was asking. And so we make a split at years below 4.5, so that's over here. And then if years is above 4.5, we do an additional split, and that is based on the value of hits. Okay, and we get 3 rectangles, R1, R2, and R3. Now the question is here, to make the link with the picture on the previous sheet, where do I get these numbers? 5.11, 6, 6.74, where do I get these numbers from? Well, if you look at this split of the feature space in these different regions, then what we're going to do is we're going to take all the orange dots in each region, and we're going to look at the salary of the baseball players in my training set, which end up in a particular region. For instance, in the region of the rectangle R1, we take all the baseball players, we look at their annual salaries, we take their log transformed values, we average them, and that's the prediction that we're going to give to any baseball player ending up in region R1. Yeah, so that's how this regression tree is going to work. So once you decided upon the splitting, once you decided upon the features that you want to use and then the cut points, the split points, then you come up with your predictions in the regression tree in this particular way. So that is my first thing, first simple example. Any questions on this? Is this more or less clear to get some intuition about the working principles of this tree? No questions from Arthur. Okay. So if you have a question, please interrupt quickly. I like that. Then I know that there is somebody listening. So if you get this intuition, then the next question to answer is, yeah, how will I build this tree? So how can I decide which features to use, which splits to make, and so on and so forth. So we're going to take a look at how that works, the process of building the regression tree. Yeah, so Said says, for points on the boundary line, how do we decide? Yeah, that's a convention that you're going to make. So here we decide to go for the strict inequality always. So that means if you end up with years exactly equal to 4.5, imagine that then we would go to the right-hand side. Yeah. So it's just a convention that you're going to make. Okay. And it's related to that. Maybe I should also stress that, like here, it also depends on whether you've got your covariates registered in, for instance, integer values or numeric values. So here you see that, I guess in the initial original data, it might be that years was registered as integers and that the split point was then taken in between two of those integer values. So it depends a bit on how you put this together exactly. And Said asks as a next question, if we have more than two covariates, how do we plot and split the space? Well, of course, you cannot plot it then anymore because you're working then in more than two-dimensional, so you will get these high-dimensional rectangles or boxes. So it's no longer, or it's not immediately clear how to, it's no longer possible to do a picture like the scatter plot that I have over here. And the way how we will be splitting, that's what I'm gonna explain now, right? So you should just see this as a very simple example to get started with. We'll see more complicated trees throughout the session. So here we go. How do we build such a regression tree? Well, so our goal is to divide the predictor space into, let's say, J, distinct and non-overlapping regions, R1, R2, up to Rj. And what is the predictor space? That's the whole space, and that's the whole set of possible values for the covariates that I have available. And like Said said, if I only have two covariates, I can easily picture this, and I see that these regions are rectangles as we know them. But of course, if P becomes very large, then I can no longer picture this, and then I have to think about the regions as sort of high-dimensional rectangles. But the important thing is that they should be distinct, non-overlapping. Yeah, so we want to do this split. And once we have this split, we're going to make for every observation in a region Rj, we're going to make the same prediction. And that's going to be with a regression tree, typically the mean of the response values for all the training observations ending up in Rj. Yeah, so that's what we did also with the example of the baseball players. So that means if you would write this model down, you would say that the prediction delivered by my tree, which I call here F3 or something, if I take the x1 up to xp values of an observation as the input, then the prediction that I'm going to deliver is going to be a y bar, and the one that I pick depends on in which region will my observation that is specified by the covariates stored in the vector x, in which region will I end up with my observation. So if I end up in region R1, then my prediction will be y1 bar. If I end up in region Rj, then my prediction will be y bar j. So the i's that you see here are indicator functions. So they are here to specify, okay, in which region do I end up. And then the y bar j here refers to the average. So the AVI is for average, the average of all my training observations, yi say, for which the xi belongs to region Rj. So that's just a mathematical representation or notation of the principle that I explained with the baseball players. You've got these different regions, and you see, okay, if I take a new input vector with covariates, in which region do I end up? And what is then the prediction that I delivered? That is the average of the outcomes that I observed in my training data for all those observations that belong to this particular region. That's how it works. Yeah. So we're now going to dive into these two, into the first step particularly. So how do we do this splitting? And once we have the splitting, then we know how to come up with a prediction. Good. So what is step one? How do we construct the regions R1 up to Rj? That's the first question. So we're going to divide our predictor space into these high-dimensional rectangles or boxes or regions or leaf nodes or whatever you would like to call them. And that's what I will denote with this R1 up to Rj. And if you look at a textbook implementation of decision trees, regression trees in general, then one mostly starts with looking at the following loss function. So then people usually say, well, we're going to construct these boxes, R1 up to Rj, such that the following residual sum of squares is minimized. Yeah. So what we're going to do here is we're going to take our outcomes on the training data. That's the yi's, where I runs over all the observations that I have in my training set. And I'm going to predict each of those training observations with the corresponding y bar Rj. And I want to minimize the error that I make when I put together these predictions. So I want to decide upon J, and I want to decide upon the specification of my regions in such a way that this residual sum of squares is minimized. That's the idea. So I have a sum here over J. So the J runs over all the boxes that I created. And then in each box, I run over all the training observations, I, that belong to this specific box. I look at their realized outcome, that's the yi, and I compare that with the prediction that my tree delivers, that is this y bar Rj. I take the square difference and I want to minimize this over the whole splitting that I created, right? So I add here in red any actuarial reflections, and that's just to point you to the fact that this is what a traditional textbook or handbook on machine learning would propose for the construction or the loss function used when constructing a regression tree. Now, of course, when we do frequency modeling, when we do severity modeling, then probably this is not going to be the most suitable loss function for us to be used. Yeah? So we're going to switch to other criteria, to other loss functions further on in this presentation. But keep in mind, this is something, this is the most obvious criterion to use for any numeric outcome y. But if you do frequency modeling, if you do severity modeling, maybe you want to replace this thing with something that is more inspired by the nature of these frequency severity data. And we're going to come to that, but not at this point. All right, so that's what we want to do. Now, of course, it's computationally infeasible to consider every possible partition of my feature space into J boxes, because I can do a lot of things, right? Because I have P features and I need to decide on where to put the splitting. So I have a lot of possible combinations that I can make. So in order to get around this, the famous CART algorithm, the classification and regression tree algorithm, is going to take a top-down greedy approach that is known as recursive binary splitting. So it's binary splitting, so we're going to ask yes/no questions, right? And it's recursive because we're going to do that over and over again. It's top-down, it starts at the top of my tree, and it's greedy because at each step we're going to make the best split at that particular step, but we're not going to look ahead, right? So maybe it's not overall the best splitting that we could make, but we just want to do it in a greedy way, and we want to be able to move down fast, let's say, to a solution. If you look into the literature, you will see other approaches. For instance, the evolutionary trees, the EV trees that we used in the pricing analytics workshop. They don't take this greedy approach, but they use a genetic algorithm to come up with a more globally optimal solution. So they don't take this top-down greedy approach. But okay, so just be aware there are different implementations, but this one is the most is the fastest one, and this is the most popular one being used, let's say. So what are we going to do the recursive binary splitting? We're going to select a predictor, xj. We're going to pick a cut point s, such that we've got the following splits. So we're going to create, we're going to move to the left, let's say, if xj is less than s. We're going to move to the right if xj is larger than or equal to s. So coming back to Said's question, I just make a choice here on where I put the strict inequality and where I allow xj to be equal to s. So it's a convention, it's a choice I make. And we're going to pick this xj and we're going to pick this s in such a way that we get the greatest possible reduction in our residual sum of squares by doing this, right? So that means that if I look at the created rectangles, call them R1 and R2, and if I'm now going to predict my y's, my outcomes ending up in R1 with y bar R1, which is the average of all the training observations ending up in R1, and if I predict those observations that end up in R2 with y bar R2, and if I look at my residual sum of squares like this, then I get the greatest possible reduction. Now, I compare this to what? Well, I started off with putting everybody in the same rectangle, in the same region, right? That would be my starting point. So initially, I predicted all my observations with the global average y bar, okay? And I had my residual sum of squares summing over all the observations doing y minus y bar squared. So if I now make this split, I'm going to look for the xj and I'm going to look for the split point s, such that if I compare my original residual sum of squares with the new one over here, that I get the greatest possible reduction by doing this split, right? So that's the principle. That's how I go for my first split point, for my first question at the top of the tree. So I look for which feature and which split point is going to lead me to the biggest possible reduction in my loss function, in this case, the residual sum of squares. Yeah, so do keep in mind that you have to compare this value for your residual sum of squares then with the value that you initially started with, and that is the residual sum of squares if you predict all the y's with the global average in your training data set. Now, how do you continue? Of course, you need to split further. So how do we repeat or how do we continue? We again look for the best predictor, for the best cut point to split our data even further. But now we do this within each of the resulting regions. Yeah, so we're just going further into these regions that we already created, and we're going to see whether we should split them any further. Okay. And this process will continue until a certain stopping criterion is reached. For instance, you can say that no region should have more than 5 observations, or you could say I'm going to stop if no region has more than 1% of my training data, etc., etc. Yeah? So in this case, I would say the way I picture it here is you're going to split in a very detailed way the whole feature space. Yeah. And of course, given that we have these different regions, we're going to predict, and that's step 2 in my building process. We're going to predict as follows. We take a test observation to which region does it belong, and then we use the mean of the training observations in that region to give us a prediction. Okay, so that's the principle. So we take a loss function, in this case the residual sum of squares, and we ask ourselves, yeah, how should I split which feature, which cut point, in order to create the biggest possible reduction in my loss function. And the way I picture it over here is you're going to repeat this process over and over, and you're going to create a very fine splitting of your feature space. The problem is, of course, that if you do it like this, so if you keep on splitting, yeah, then you will end up with leaf nodes where you have very few training observations. So you are creating a model that is overfitting. Okay, so that will be the next topic to discuss. So how do we prevent this tree from overfitting? But first, let me check any questions on this. So the building process for the regression trees. So Said says, the algorithm is somehow similar to k-means clustering. Yeah, in a sense, perhaps, but here we clearly have this target value, the y. So here the loss function is really defined for the target values and the prediction delivered for our target values. Whereas if you look at k-means, it's more about finding similarities between observations based on their feature values. So that's a difference. The focus on a target versus the focus on similarity. Any other questions? If not, let me continue a bit more before the break. So this is a good point to reflect a little bit about these loss functions. So I already said we're using here, in the way I presented the algorithm, we're using the residual sum of squares and with acronym RSS. So what are some alternatives there? Well, in any case, you can use more generally a loss function L, let's say, and in this loss function, I will always use my outcome Y and the prediction delivered by my algorithm, which I denote here very generally as F evaluated in Xi, right? So when we're using a loss function, we want to split our predictor space such that if I would split, if I would make the distinction between those observations ending up in R1 are predicted with Y bar R1, and those observations I ending up in region R2 are predicted with Y bar R2. So if I evaluate the loss function like that, I want to minimize this loss function, right? So I want to make sure that by making this distinction between R1 and R2, I get the greatest possible reduction in my loss function. Okay. So that's what we keep in mind. And in the classic case with residual sum of squares, the loss function is just going to be the square difference. Okay. But now I can think about, can I come up with any other loss functions which will allow me to generalize this idea to outcomes that are not necessarily numeric on a continuous scale. Okay, and what we're going to do here is we're going to rely on the notion of a deviance or a scale deviance in the way or in the sense how we introduced it in the class of generalized linear models. Yeah? So think again, what was this deviance? In this deviance, we compared the likelihood evaluated in the fitted model with the likelihood of a saturated model. Yeah, so the Ly that I denote here is my likelihood of my saturated model, and the LFX would be my model likelihood. Yeah? So what we want to do is we want to come up with a loss function, L, such that I can see this deviance as the sum of individual contributions from my observations in the training data, individual contributions of a certain loss function L, such that altogether they form the deviance. Yeah, so that's the inspiration that we take. So if I look at, for instance, a Poisson regression model, I can write down this deviance and I see that it reduces to a sum of individual contributions to this deviance. And then I can use this building block, I can use that as a suitable loss function for training a regression tree calibrated to a set of frequency data. So that's the idea that we're going to take. For instance, if I do this with Poisson, I can work out the expression for the deviance. So this is something we've seen before. And I see indeed it reduces to a sum over I of certain individual contributions of each observation I in the training data set to this deviance. So that inspires me to go for a loss function L when I'm looking at frequency data, a loss function L that is really inspired by the expression of this Poisson deviance. And this is what I'm going to do then. This is what I'm going to use. This is my loss function that I could use when building a regression tree for frequency outcomes. And it's a loss function that is directly inspired by the expression for the Poisson deviance. Yeah? There's a little tweak in here. I could put weights. Yeah, so I just allowed this possibility here. So if you put in weights, it means you will give a weight to each contribution, to the contribution of each observation to your total loss, let's say, and that's denoted here with the double, the WI. You have to be a little bit careful if you're building these tree-based machine learning methods. You have to be careful if there is an exposure involved. Yeah? So we know how to deal with exposure from our classes on GLMs and our GAMs. Well, here it's typically possible to do so, but you have to be very careful that you that you do it correctly and that you take the exposure into account when delivering predictions and so on and so forth. So just at this point, it's enough that you should be aware that if there is an exposure measure D, that we're going to work with predictions specified as D, the exposure, times f of x. So typically f of x here is the prediction that we're going to deliver for a full year of exposure. And if we want to change that, we should take it into account explicitly. So I'm going to explain you in the tutorials with R how to do this. But just be aware that in general, it's possible to take it into account, but you have to be a bit careful. Yeah. So that's for the Poisson, that's for the loss function inspired by the Poisson deviance. We could go a bit further. We could say, what about the normal deviance? Yeah. So also for the normal distribution, we can work out our deviance. We see that the deviance can be written like this. And so we see that very naturally, the loss function inspired by the normal deviance would be the squared error loss, right? So here, immediately you see that if you use this residual sum of squares, if you use this squared error loss, then in fact, you are assuming under the hood that you're working with a model with a normal deviance. Yeah. So if that model assumption does not make sense for your data, then it's better to switch to another type of deviance statistic. Let it be Poisson, let it be gamma, let it be log normal, and to use that as the loss function to train your tree-based machine learning technique. Yeah. So here I went through two examples, Poisson deviance, normal deviance. If you look at the paper that I did with Roel, you will also find there the expressions for the gamma deviance, for the log normal deviance. So that is possible as well. So the main takeaway here is be careful if you're going to do this with insurance data or with frequency severity data in general. Think a moment about which loss function do you want to use. And typically, you can switch to either a Poisson or to a gamma deviance, etc. But it's typically not discussed quite extensively in the mainstream literature on machine learning techniques, because of course this frequency severity setting that's very particular for the context that we are working in. Okay, and I just want to make you one comment, and I'm going to switch my screen for that. But of course, if you say I want to switch my where did I put it? I want to switch my loss function. I want to change my loss function to something else. Then this is what I wanted to show you. In many of the packages, or in some of the packages available in R and Python to do this tree-based learning, you will, in some of the packages, you will find this Poisson deviance loss function. You will find this gamma deviance loss function, but not in all of them. So for instance, if you want to do random forests in R and you want to use a Poisson deviance as the loss function, you want to switch to a gamma deviance. That's, for instance, not available in the standard implementation for random forest available in R. So part of the work that Roel did for his PhD is to fill these gaps. And so we, a couple of weeks ago, we put the dist R forest package online, which allows you then to switch your to certain distribution-based loss functions and to use them in the R part implementation available in R. So this allows us to run or to build regression trees, to build random forests, bagging with loss functions that are more suitable to the actuarial applications that we have in mind. So that's a comment that I want to make. Not all these loss functions that we love to use as actuaries are directly available in the standard R and Python implementations that you can find online for these tree-based learners. Some of the gaps have been filled by the work of our group, particularly with respect to the use of these loss functions. Extra considerations. First of all, about finding the split points. Well, that is working straightforward. I mean, it's a computationally interesting problem, let's say, but it's rather straightforward to solve if you have continuous predictors. Continuous predictors that can be ordered in a natural way. Now, think about the years and the hits covariates. Think about a covariate like age of the policyholder. We can do that, right? But things get a bit more complicated if you're looking at categorical predictors. Now, if these categorical predictors have a few levels, think about a binary predictor, for instance, male or female, then it's also easy to consider the different possible splits that you can make. You can ask the question, is my policyholder a male driver, yes or no? That's an easy question to investigate. But if you have so-called multi-level factor variables, and these are factor variables or categorical variables, where you have a lot of different levels. So say you have Q levels, then with combinatorics, you can show that there are 2 to the power q minus 1 possible partitions into 2 groups which are non-empty. So you see that if the Q becomes large, then you've got a lot of different possible splits into 2 groups. Too many to investigate in this algorithm. So this might create a problem if we're dealing, for instance, with postal codes. Yeah? So if you look at postal codes, then we saw in the pricing workshop that you have 1146 different postal codes in Belgium. So if you would process this variable postal code in the same way as we're doing with a continuous, as we're doing with the predictors as explained so far, then you would have to investigate all the possible splits into 2 non-empty groups of all these different postal codes available. So that's not going to work. So what this kind of algorithm will do, and we will be coming to that when discussing the R-part implementation, but we're going to make a so-called encoding or embedding, and we're going to replace then the categorical predictor with a numerical predictor, yeah, in case the number of levels becomes too high. So for instance, you can replace your postal code categorical covariant then with the empirical claim frequency that you would observe for each of the postal codes in your data. So that's a kind of a shortcut that is taken here in order to avoid these combinatorial splitting problems, which are too hard to tackle in the algorithm. So the whole use of encodings and embeddings, I also posted a thesis topic on that, but that's exactly what would be happening here. You would replace the categorical variable with a numerical equivalent, so to say. With postal codes, you can also do it slightly different. You could go for the lat and the longitude coordinates of the center of the postal code. These are numeric, so you can do the splitting of these numerical variables then as well. So there are different options here, but keep in mind that this is something that you can study in more detail. This is something that could create potentially some problems, or when you have to take a certain approach, the kind of encoding that you're going to use in order to get around this problem in the implementation. Yeah, so that's a comment that I wanted to make. And with this multi-level factor here, what I mean is a factor variable with a lot of levels. Think postal code, think vehicle type, think brand of the vehicle, think the NACE code representing the industry in which you're working, and so on and so forth. Okay. All right, let's get back then to our building process, because in the way how I explained it so far, we were building a tree and we were splitting and splitting and splitting and splitting until none of our end nodes, our leaf nodes, were having, let's say, more than 5 observations. So the process as we sketched it so far is going to overfit our data, because it's going to create very small leaf nodes. So it's really picking up the noise in our training data next to the signal that we want to pick up. Yeah. So what are we going to do? There have been, or several solutions to this have been investigated in this literature on tree modeling. And one of the first strategies was let's build the tree as long as it's creating a decrease in the residual sum of squares that exceeds some specific threshold. Yeah. And in a way, you can compare this with what we did with the GLMs, where we said, yeah, the improvement in the deviance and the drop in the deviance should be significantly high and should be higher than a particular quantile from a chi-square distribution. So people have been working with that kind of reasoning in these in the building process of trees as well. But the strategy that is nowadays mostly followed is that we're going to grow a very large tree. We're going to create it, we're going to label it as T0, and we're going to prune the tree to obtain a specific sub-tree that is satisfying or that is optimizing a certain criterion. And we call this cost complexity pruning. So that's what we're going to explain as the next step. That's the strategy that the current implementations of building trees in R or in Python are following. So for the Dutch-speaking students, pruning the tree, that means that the boom gaat snoeien. So you're going to cut out some branches, some nodes, so that you get a smaller tree in the end. Yeah? And the reason why you want to do this is because if you wouldn't stop splitting, you would create a model that is going to completely overfit your available data. So here is the strategy. We're going to look at a sequence of trees indexed by a tuning parameter. I'm going to denote it here first with alpha, following the book, An Introduction to Statistical Learning. And for each value of alpha, there is a subtree T available in the big tree that I started with, such that this subtree is going to minimize the loss function, which starts from my residual sum of squares once again, but now adds a penalty for complexity. And this penalty is going to take into account the size of my tree. And the size of my tree is denoted here with the T between these bars. And it's going to count the number of leaf nodes in my tree. So it's going to count in how many regions did I split up my feature space. So for each value of alpha, there is a subtree. I can prove that mathematically. There is a subtree T, which is constructed by starting from this T0 and by cutting out cutting away some branches. There is a subtree that minimizes this penalized criterion. Yeah. So what do we see here? The T between the brackets, that's my number of terminal nodes for the tree. And once again, the Y bar Rj, that's the predicted response associated with Rj, right? So you also see if I let the alpha go to 0 here, then the penalty for complexity is going away, right? And then I'm back with my original loss function, which is going to overfit my data. If I let the alpha become large, then I should push, then my tree has to become small in order to find the tree that's going to optimize this criterion. Yeah? So we've seen that before, that you have a certain loss function, you add a certain penalty for complexity, and there is this tuning parameter that is going to decide on how strong or how much weight, in a sense, do I give to this penalty. And this alpha, that's a parameter for which we do not have an analytical expression available. So we'll need to rely on the techniques discussed in previous class, the techniques of resampling and working with k-fold cross-validation and so on. We're going to use that kind of methodology to decide upon the value that this alpha should take. Yeah, so more on that later on. So here we are. The tuning parameter controls the trade-off between the subtree's complexity and its fit to the training data. If you have an alpha equal to 0, your subtree is going to be the large tree that you started from. And if the alpha becomes large, there is a price to pay for having a tree with many terminal nodes. And then this tree with many terminal nodes will not optimize the penalized criterion. Okay. So we pick a value for alpha, we tune the parameter alpha using the validation set approach that we discussed in the last class, or using the strategy of k-fold cross-validation. So we're going to see that later on. When we return to the full data, so once we picked a meaningful value for alpha, we can return to the full data. We can pick the subtree that is corresponding to this particular value for alpha. So to picture this in my hitters example, this here on the left-hand side, you see the unpruned tree, right? So that means I went on splitting and splitting, and I used a lot of different covariates. I end up with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 leaf nodes, right? So this is a very detailed tree. You also see that, I didn't mention that, but in picturing this tree, you see that this branch is taking, is large, it's taking a large part, a substantial part of my visualization here. And that part is proportional to the drop in the loss function that this split is creating, right? So you see the split on years is really the most important split. And you also see that these last splits over here, that they don't improve my loss function substantially anymore, right? So the very important covariates here, they typically end up high in my tree. They're picked as one of the first splits. And they can also be picked up multiple times in the tree. Because if you do a split here on years, you'll see that years is used as another split over here. So you can do multiple splits on the same covariate as well. If we prune this tree, we're ending up with a tree with only 3 end nodes. And you see that it's the first split here and the split here on the right-hand side. These are retained, and the other splits are removed in the pruning process. So how did we decide on why do we end up with 3 end nodes? Well, that's been done with this strategy of validation, cross-validation. And in this case, following the book, An Introduction to Statistical Learning, in this case, the data set available was split into 2. 132 observations were used in the training set, 131 in the test set. And then we built, or a large tree was built on the training data. Alpha was changed to create different subtrees. And 6-fold cross-validation was used on this training data set. And the MSE was estimated in a cross-validated way and pictured as a function of alpha. So why is it 6-fold cross-validation? You may wonder about that, but that's because my training data has 132 observations, which I can divide by 6 and create groups of equal size. So that was the strategy taken here. So if I picture the results, I'll get something, I get a curve like this. So this is like the hockey stick or the U-shaped curves that we discussed earlier on. So if I look at the black line, this is my training data, right? So for the black line, you'll see that if I make the size of the tree larger, then I can push this training error to 0 in principle. So I can make it, let it decrease and decrease and so on. If I look at the cross-validated error, that's in green, then you'll see that if I start to increase the size of the tree, this cross-validated error is gonna increase, right? So here you have a kind of U-shape available. And the same phenomenon is observed on the test set. So here I have a separate test set on which I can evaluate the constructed tree. We've got with the bullets or the dots, we've got the mean over the different folds that we created. We also got the bar which represents the corresponding standard error. We mentioned that earlier on. And the reason why you also have these dots and these bars, for instance, with the test error here and with the training, is because you can repeat this experiment, the splitting into 132 observations, 131 as test observations. You can repeat this experiment a couple of times and keep track of the training error, the test error, and so on and so forth. So that's what happened here under the hood of this picture. So what do we want to get out of this picture? If we look at the cross-validated error, where is this one minimal? So you'll see that with a tree size equal to 3, we reach the minimum, and afterwards our cross-validated error is going to increase again. So that's why in this particular example with the hitters data set, you go for a tree of size 3. And then the optimal tree was the one that we pictured over here. This is a tree with size equal to 3 because it has 3 endnodes. So that's how we come to this final pruned tree via the so-called cost complexity pruning. Okay, so this is important. There is one tuning parameter to keep in mind here, and that's my alpha in the notation that I used so far. That's the parameter that determines the trade-off between the goodness of fit and the complexity of my tree. Yeah. Now, just to give you one outlook towards the implementation in R of such trees. Well, in R, the go-to routine is the rpart package, where rpart stands for recursive partitioning. And in rpart, the optimization criterion is expressed like this. So I mentioned this because it's not in the form alpha times the size of a tree. Yeah. So it does take the size of the tree into account. That's the J in this notation. That's the number of regions that we end up with. But this J is scaled with the initial loss function. And with the initial loss function, I mean the loss function that you get when you predict every outcome Y with the global average. And the reason why it's done in this way is because then you can refer to this cost complexity parameter, CP, where if the CP is equal to 0, you'll get the biggest tree possible. But if the CP is equal to 1, you can show mathematically that you will end up with a root tree that is not splitting. So a root tree that realizes this particular loss function. So that's why rpart is using this rescaled penalty, if you want, so that we've got a nice range of possible cost complexity parameters, the CPs to investigate. Namely, our CP will range from 0 to 1, where the two boundary points lead us either to a very large tree or the smallest tree possible. That is the tree with only the root, that is the root tree, so the tree that does not do any splitting. Yeah, so that's why rpart is going to follow this specification. So what are we going to do? We're going to do a tuning strategy. We're going to do a search grid to find the optimal value for the CP, use cross-validation tools to evaluate the performance of the tree on new data, valued across different values for this CP parameter. Yeah, but we're going to come to that when we dive into in the tutorials. Okay. Just to show you a bigger tree, this is again our MTPL dataset studied in the pricing analytics workshop. This is the frequency part of the MTPL dataset. And this is the tree that is constructed in rules paper, so based on a nice, an extensive tuning strategy, good evaluation, and so on and so forth. You also see that you can nicely visualize this model. So if I would ask you, is this an interpretable model? Yes, it is, because I can clearly see which decisions are made by the tree and how this tree constructs a certain predicted value. So we distinguish here, or we discover here, which features are used by this frequency tree made for the MTPL data. So it's the bonus malus level occupied, it's the age of the policyholder, it's the age of the car, the type of fuel, the longitude coordinate, so that has to do with the spatial information, and the gender of my policyholder. And so that's what's being used in this tree, and that to quite quite some extent corresponds with the variables that we've been using when we were constructing GLMs and GAMs for this data set. Yeah, so there also we used the BM, the age of the policyholder. I'm not sure if we used the age of the car. I don't remember by heart, but we're going to get into this comparison between what the tree does, what my GLMs do in the next class. If you look at the end nodes here, you get a prediction for the annual expected number of claims. So this is annual. So the exposure has been taken into account in this whole model building process. But the prediction that you get at the end here is just my f of x. So if I want to take exposure into account in my predictions, I should still multiply here with the exposure values. But in the model building process, I'm going to correctly take the exposure into account, as we will see later on. Yeah, so that's what a tree would do for this data set. So brief discussion, some advantages and some disadvantages. Trees are easy to explain in the sense that you can picture what the model is doing, so that's super simple. They closely mirror human decision making because you've got this flow chart with yes or no questions. The trees can be displayed graphically, can be interpreted easily by a non-expert. They can handle qualitative predictors, but if the levels get too high, the number of levels get too high, they'll take a shortcut. But what is the essential argument, let's say, against using a simple tree? That is that they generally do not have the same level of predictive accuracy as some of the other modeling techniques that we will discuss today and that we've been discussing in the past. So in the paper with Roel, we make a very extensive comparison in terms of predictive accuracy. We compare GLMs, GAMs, trees, random forests, gradient boosting machines, and so on. And there you will also see that the tree is like the one that is performing worse in terms of the predictive accuracy that you can realize. So it's a very simple method, but on itself, it's probably not a good idea to use it in sophisticated predictive modeling problems. Yeah. Any questions? Because that's what I wanted to say about the trees. Any feedback? If not, that's okay. So I see a few comments popping up. Okay. Thank you, Arthur, Anneliese. Seems to be clear. Good. So we went through the construction of a tree, spent quite a bit of time on it because that's something we really need to continue our discussion of the next techniques. Yeah. So we're going to go and we're going to combine small trees, or no, we're going to combine different trees together. And the reason we're going to do that is as follows. We want to improve our predictive performance, and we want to also improve, let's say, we want to create a less variable prediction compared to what a single tree would do for us. So we're going to dive into 3 methods called bagging, random forest, and boosting. The first 2, they really belong together, so they are quite similar in the working principles, bagging and random forests. And then the boosting takes a different kind of idea, and that's what I'm going to continue with right now. So first of all, let me picture the idea of bagging. So it's difficult to understand at this point, but after the class, go back to this visual, because that's what you should try to understand. So if we do bagging, the idea is that we're going to create different data sets of our initial data. And we're going to use the idea of bootstrapping for that. Yeah. So we're going to create bootstrap data sets We're going to create a big tree for each of the bootstrapped data sets. This tree is going to deliver us a certain prediction. And what we're going to do in the end is we're going to average all the available results and come to a final answer. And it turns out that that helps us to improve the predictive accuracy of our technique compared to building a single tree. And it's also going to reduce the variability of a single tree. So that's the idea of bagging. It's bootstrap aggregating. Yeah, that's the essential. So my explanation can go quite fast. And like I said, after the explanation, please come back to this visual and think about it for another couple of seconds. So a natural way to reduce the variance and to increase the prediction accuracy of a statistical learning method is to use many training sets from your population to build a separate prediction model using each training set and to average the resulting predictions. Yeah. So it turns out that that helps you to reduce the variability of your predictor, and it also helps you to increase the prediction accuracy. Now you can do that, of course, with any kind of technique. It's not restricted to using trees. You can do that with GLMs if you want, or with GAMs. You could do this principle with any kind of learner you want to consider. Yeah. So what are we going to do? How would I write this down with a bit of a mathematical notation? I would create different models of different learners indexed here with T going from 1 up to capital T. And I would construct each of the learners on a different training set. Yeah? And in the end, what is my bagged model going to deliver me? It's going to deliver me the averaged prediction. That's what I want to do at this point. Yeah. But usually, of course, you do not have access to these multiple training sets. You only have one bucket of data, let's say, and that's what you have to use. And that's where the idea of bootstrapping is going to come in. We want to create these artificial training sets out of the initial available training data. So that's what we're going to do. We're going to create T different bootstrapped training data sets from the initial data. And I'm going to denote them here with calligraphic DT. So that's a bootstrap data set out of my initial data set calligraphic D that I have available. And we're going to train our methods on the teeth bootstrapped training set and construct a tree on this data set. And in the end, we're going to average all our predictions. So that's the strategy that we're going to take here. So think again about my visual. I juggled around with my data set. I created a new training data. I create a tree on that. I do this T times, and I take the average prediction. That's what bagging is going to do for me. So remember what bootstrap was? I think we mentioned it in the class before the break. So when you're bootstrapping your training data, you are picking observations at random from the original training data set, but with replacement. Yeah? So you can pick a certain record multiple times when creating a bootstrap copy of your original data set. Yeah? So the name bagging is coming from bootstrap aggregating, because you do the bootstrapping and you do the aggregating of the different base learners. And this idea goes back to the work of Leo Breiman in 1996. And the focus here is particularly on reducing the variability of the technique of the learner that you create. Because that's one of the things, if you would do a tree on a given data set, if you take a different training data set from this available data, your tree might look quite different. So a tree is known to be a modeling technique with a high variability. Yeah? So if you build the tree on a different part of the data, the tree might look quite different. And that's of course a drawback of this technique, So one of the reasons why this bagging method was introduced was to reduce this variability. And here the idea is, if you would look at the variability of the mean here, you would get 1 divided by t squared multiplied with t times the variability of a single tree if they're all independent from each other. So there you see that by taking more and more trees, so by enlarging the capital T, your variability will be reduced. And that's the idea of the variability of the sample mean. You can reduce that by averaging over more instances. So that's the essential idea. Okay, so I hope this notation is clear. So the calligraphic DT refers to the bootstrapped copy of my data, and the F3 refers to building a tree on this particular bootstrapped training set. Yeah. Now, what are some general recommendations if you do this bagging? The T trees are growing deep; they are not pruned to decorrelate the trees. So if you go into this literature, you will see that there is no danger for overfitting here if you would let the trees grow deep. Yeah? So some authors say you shouldn't train this parameter T. You can go for a very large number. You can increase this number of trees as you want, and there is no danger for overfitting here. It's a good thing, because then if you build larger trees, you will have more nuances, differences in the trees, and that helps to decorrelate the trees over which you are averaging. On the other hand, another suggestion in the literature is that instead of using a bootstrap sample of size n, the original number of observations available, you can also introduce some extra randomness by picking a bootstrap sample of smaller size, delta times n, where the delta is a number between 0 and 1. And because then you build even more differences in your training data, leading to more different constructed trees, so more decorrelated trees, and that helps to reduce the variability and that helps to reduce the variability of your averaged prediction. But this also helps, of course, to reduce the training time, the computational time. So that tweak is often also put into practice when you are building such a backed model. Yeah, so these two recommendations are generally taken into account. If we do bagging with regression trees, we're just going to average the resulting predictions constructed by each of the trees in this bagged model. If we do bagging with classification trees, so if each tree is going to deliver a yes or no prediction, then how are we going to put them all together? Well, what we're going to do is we're going to record the class predicted by each of the composing trees, and we're going to take a majority vote. So that was also the case in this visual that I had, where we were predicting grapes and some other type of fruit. In 2 out of the 3 cases, we predicted a certain type of fruit, and in 1 of the 3 cases, another kind of fruit. So here we would go for this majority vote. So which prediction is coming up most often? So I mentioned this, bagging with regression trees, bagging with classification trees or decision trees, just so you know. All right. And I think we're just going to continue with the random forest, because this is super close to what bagging is doing. So random forests provide us another improvement over bagged trees by means of a small tweak, of which the motivation is again to further decorrelate the trees. And what we're doing in random forests is we'll keep the whole principle of bagging. So we're gonna work again with trees constructed on bootstrapped training samples. But each time we consider a split in the tree, we're going to pick a random sample of m of our predictors out of the full set of p predictors that we have available. Yeah. So we're going to bring in further differences, decorrelation, by making the trees look quite differently. And here we're going to do this by saying whenever you do a split, you cannot use the whole set of features which are available, p features available, but you have to pick m out of p features at random. And that's exactly going to tackle the problem, if you want, that Jonathan described. Because if you have a very important predictor, it's probably always going to be picked as the first one to split on, or it's going to be picked up very often to split on. And if you build in this extra randomness, then at least you will construct certain trees which are not using this strong predictor as the first one to split on, because this predictor was then not part of the set of split candidates m with size m that were chosen at random from the available split candidates. Yeah. The general recommendation is to either consider m as a tuning parameter or to use an m approximately equal to the square root of p. You find different guidelines there in the literature. In our work, we considered the m as a tuning parameter. So the rationale, as I already mentioned, if there is a very strong predictor in the data set, you will see that in your collection of trees, most or all of the trees will use the predictor as the top split, and the back trees will look quite similar to each other. And the predictions are highly correlated. There is no substantial reduction in the variance compared to a single tree, so we're not able to add much on top of what a single tree would do. So this brings us to, yeah, we have to do something about it. That's why these random forests have been introduced. Yeah, so the random forests overcome this problem. So that's all there is to say. I end the section on random forests with a screenshot from our paper with Roel. So if you look at this procedure, algorithm 1. So what are we doing here? We have a loop over t, the number of trees to be constructed. We generate bootstrap data, delta or calligraphic dt. We do them of size delta times n, so that's to bring in an extra randomness. We sample with replacement from the original data. We're gonna do we're gonna build a tree, so that's gonna happen over here, and we're gonna build this tree by randomly selecting m of the p variables which are available. We're gonna look for the optimal splitting variable from the m options together with the selected cutoff point c, and so on and so forth. So we construct in each step t, we construct this tree f tree on the bootstrap copy of my data set, and in the end, the prediction that my random forest is going to deliver is then the average over the predictions that these different trees have been constructing. So what did we consider here as the tuning parameters? Well, in our paper, we tuned the number of trees, the capital T, and we tuned m, the number of split candidates. Yeah, you could take there a different approach, and you could say, I don't care about the tree, I just let them become very large. I don't care about the m, I just take the heuristic that m is equal to square root p. But we did it a bit more evolved and tuned these two parameters. What is very important to keep in mind is that the trees are here independently from each other. So you can run them, you can build them in parallel. They don't rely on any information shared. They're really independent from each other. And the goal, the reason why we do this is because we want to come to this average prediction, which is on the one hand, reaching a higher level of predictive accuracy, and on the other hand, is reducing the variability compared to what a single tree would do. So that's what I wanted to say. about the random forests. Any questions? Let me just peek. Yeah, we're going to continue with boosting from here on. Any questions? If you look at the implementation, I already mentioned that, but you have to be a bit careful there. If you have a package in R or in Python that does the random forests, if you want to do this with frequency data, if you want to do this with severity data, then you would have to see whether you can find a suitable loss function in this package that you prefer to use, a suitable loss function that can handle the frequency severity data. So Roel designed the package to do this with R for some popular loss functions in actuarial work. Good. Okay, that brings us to the last algorithm to be discussed today, and that's the algorithm of boosting. So here you see immediately from the visual that we're going to do things a little bit differently, in the sense that we're going to work with a sequential approach. Whereas with the bagging, we started here with constructions of trees in parallel, and then we averaged those trees. Here we're going to do it in a different way, and that's very important to realize from the beginning. Here we're going to work with a first tree. Then we're going to say we're sort of looking at a new data set where we give priority to the cases on which our previous algorithm was not working quite well. We're going to construct a tree for this new data. We're again going to look, okay, for which cases did things do not work out very well. We're going to construct a tree for them, and so on and so forth. Yeah? So we're really working sequentially here. We're going to rely on the predictions that were developed in the previous step of the algorithm. This also means that if you keep on going, if you keep on repeating the same recipe, you will be overfitting. Because you're always going to look, okay, in which area did my tree did not work well, I'm going to improve the algorithm there, and so on and so forth. So here, the point at which you stop the algorithm, so the number of trees that you construct, will become very important. That will become an essential tuning parameter in this boosting approach. Yeah. So it's a consecutive approach in contrast to random forests, because the random forests are working in parallel. So what is the idea? So boosting is an iterative method that combines many weak learners into a more powerful prediction. And so it's called boosting because the idea is to boost your weak learner. And the weak learner, that can be quite a different set of algorithms. But what we're going to discuss is, as a weak learner, we take a very simple regression tree with just a couple of splits. And so with a depth equal to 1 or a depth equal to 2 or to 3, that's the kind of weak learner that we have in mind. Why do we use the decision trees? Because they're super simple. They're super simple to work with, to build, and to take an average prediction from. Yeah, so that's the idea. You take a weak learner, in casu a simple decision tree with only a few splits, and you're going to boost this weak learner. The boosting methodology, and then particularly the stochastic gradient boosting machines, they're often considered as one of the most powerful shallow machine learning techniques. So if you go to competitions like Kaggle competitions and so on, then the gradient boosting will be used a lot, or will be one of the algorithms that people typically are working with, or that people take as an ingredient to perform or to improve the predictions even further. Yeah. So we're going to focus on boosting with trees. I put here decision trees, but it's better to call it regression trees. That's what we're going to do. And keep in mind, as I mentioned when discussing the previous slide, the trees are growing sequentially. So each tree will be grown using information from the previous tree. That's very important. That's also the main distinction with the approach of random forests. We're going to talk about the boosting algorithm. First, we're going to talk about the general principles of boosting, and then focus on stochastic gradient boosting machines, which use small trees, simple trees, as their base learners. That's the idea. Yeah. So I'm going to pick it up again from sheet 38. First, with a bit of history on these boosting algorithms. So, what can we say here? Well, in the early 90s, these boosting algorithms appeared, combining or boosting a number of weak classifiers. So it was initially designed as a classification technique. So putting together these weak classifiers into what is called an ensemble classifier, which was able to achieve a better misclassification error rate. So there are a few important terms in this sentence. We talk about a weak classifier and create an ensemble. Putting these different classifiers together, we create an ensemble which is capable of predicting the problem at hand in a better way. Yeah. So AdaBoost was the famous algorithm then in 1999, which then brought an effective computer implementation of these ideas, which were going around for a while at that time. Now, the step then from AdaBoost to the to the gradient boosting, as we will discuss it today, was then launched by the work of Friedman et al. In 2000, because this paper connected the idea of AdaBoost to the statistical concepts of a loss function, of additive modeling, of logistic regression as we know it. More particularly, that paper interpreted the AdaBoost, gave an interpretation to this AdaBoost as a forward stage-wise additive model, minimizing an exponential loss function. So that's a lot. So I will explain that a little bit more into detail. But the whole idea is that nowadays we have access to these boosting methods, and we can formulate these boosting methods really starting from a loss function that we wish to minimize, and we're going to create an ensemble prediction method by adding certain weak learners together. Yeah? And again, the loss functions that we can use, we could look at a squared error loss, but we could use also more a Poisson deviance inspired loss function, a loss function inspired by gamma deviance, and so on. And you see here one other loss function mentioned, this exponential loss. We didn't discuss that yet, but that is a loss function that you could use for classification problems. Yeah? So let's dive a bit more into this. So this understanding, the fact that you could see this AdaBoost also as a technique that is minimizing a loss function, that is working in a forward additive way, and so on, that really led to a new perspective on this boosting algorithm, enabling several extensions. And that was eventually what led us to the work of Friedman in 2001 on gradient boosting machines with GBMs. That's the one that we will use today. You can use those for classification as well as regression problems. We're going to use them with trees because those make an excellent weak or base learner for boosting. Why? Because they're simple. You can easily add the predictions together and they're easy to use and to construct. We can remedy greediness by employing shrinkage or regularization. So we're going to talk about that a little bit more. But that has to do with the fact that you can quickly overfit, or that you can quickly work too hard with this kind of learning method. So you want to take small steps in improving the prediction obtained in the previous step. That's why we often use this shrinkage principle. But we're going to discuss that in more detail. Now, what about then the step from gradient boosting machine to stochastic gradient boosting machine? Well, that was an extension by Friedman in 2002, which was in fact inspired by this idea of bagging. And the step towards stochastic gradient boosting implies that you're not going to use the training data set as it is given, but that you're going to do you're going to make a sample, say of size delta times n, where delta is a number between 0 and 1. You take a random sample from this available training data, and as such you create extra randomness, and that helps to further improve your predictive accuracy. So that's the same kind of idea as we saw with the random forest, where we also took this bootstrap sample, in that case, of size delta times n. Okay, so a few more details before we can present the GBM algorithm as we're going to use it in the next sessions. So let us first think a little bit about this connection between boosting and forward stage-wise additive modeling. Yeah. So how to see this? Well, let me explain this with the connection of to forward stepwise linear regression. So what are you going to do if you construct a so-called forward stepwise regression model? Then you take a response y, you have a certain set of predictors x1 up to xp available, and you're going to look for the xj that gives you the smallest, so the biggest reduction, the smallest residual sum of squares, when you build a regression model of y on xj. Yeah, so you're going to pick one particular covariate. You're going to do the linear regression of y on this covariate xj, and you pick the covariate that leads to the biggest reduction in the residual sum of squares. And how are you going to continue? Then you're going to pick in the next step the xk, such that you get again the smallest additional residual sum of squares. If you now do the regression of the residuals from the previous step on this xk, right? So the trick is here that you're going to see where did the model from my step 1 did not perform well. So let me look at the residuals constructed from the model in the first step, and let me build a regression of these residuals on xk. That's how I will continue, right? So we're going to repeat these steps. So this is the idea of forward stepwise linear regression. And this also means that the final prediction that you constructed, in fact, by adding the prediction beta j hat times xj from the first step, adding it, or you add to that the prediction in the second step, so that's the beta hat k times xk, and so on and so forth. So you get an additive model here. You do it in a forward way, you do it in a stepwise way. Yeah, so keep that in mind, because you could say, okay, if I do not want to stick to linear regression, then I can generalize this way of thinking, and I can say, let me build an additive model using a certain set of basis functions. And basis functions is here very, very broad. So it could be anything that relies on the input variables x that I have available. Yeah. It's additive, so it adds certain components together. So that's also what we had when we talked about generalized additive models. We also said the predictor is an additive predictor because it adds like linear components with smooth functions in multiple dimensions and so on. So that's the idea here. So let us say we want to build a certain predictor, f of x. Yeah, here I put the x in bold and here I didn't do that, so that's a typo, but I mean the same thing. So it's f evaluated in an input vector x, and this model is constructed with this additive expression using basis functions. Yeah. So what I'm going to do then is I'm I want to come up with this expression by minimizing a certain loss function over training data. So what do I want to do? I want to find the parameters beta m here, and I want to find the parameters gamma m, which are used by my basis functions, and I want to make sure that this problem is minimized. And again, this loss function could be a residual sum of squares, it could be a Poisson deviance, it could be something that is suitable for the problem that I wish to work with, right? So this is a very, very general problem, a very broad problem that is, of course, very hard to solve. So to make it more computationally feasible, we can focus on getting just a single basis function, yeah, instead of this sum. We could focus in each step on getting a single basis function and find the beta and the gamma that we should use over here in order to minimize this loss function. Okay. So what is then this very general forward stage-wise additive approach? Well, if you work with the squared error loss, so y minus f of x squared, and if you look at your stage-wise additive model, then what you're going to do is you're going to look for the beta and the gamma and the basis function, such that if you add this new guy to the prediction that you achieved in the previous step, denoted with fm minus 1 evaluated in x, such that this loss function is minimized. Yeah? But now here, because you're working with the squared error loss, the residual then obtained in step m, or the residual that you have at the beginning of step m, so the residual that is using the available observations y and the model achieved in the previous step m minus 1, this residual is going to come up very natural, right? So when you say, I want to build my model like this in a forward stage-wise additive way, and if I'm relying on the squared error loss function, I'll get this very natural and intuitive interpretation that says, then you're building a model for the residuals from the previous step. And you want to improve your model by finding a good approximation for these residuals from the previous step. So that's the general principle of this forward stage-wise additive model. And then, of course, the forward stepwise linear regression. That's just a simple example of this general approach, because then you restrict your basis functions to be of the form beta times a certain feature from the set of features that you have at your disposal. So why this whole story? Because it's on the next sheet we will see that this ADA boost was really proposed then at the beginning of the Nillies, really by taking this idea and by saying, yes, I can see this ADA boost as an example of this forward stage-wise additive thinking with a particular choice of the loss function, not the squared error loss, but the exponential loss function. And I want to mention it here because here you see, and that's a very important observation to start with, you see that if I do squared error loss, and if I apply this forward stage-wise additive thinking, then I'm essentially building a model for the residuals from the previous step of my model. But that observation only holds for the squared error loss. If I would be using Poisson deviance, then that would not be the case, for instance. Yeah? So that's why when we really go to the algorithm of gradient boosting, that gradient will come in. Yeah? So you'll need that gradient as a generalization of the idea of the residual that you see coming up here quite easily if you're working with squared error loss function. Okay, good. So let me go a little bit further and then take your questions. So when we go back to the ADA boost algorithm, so ADA boost turned out to be equivalent to forward stage-wise additive modeling with a particular choice of the loss function, namely the exponential loss function. Yeah? And the idea was there that it's a classifier, so AdaBoost is a classifier. So the idea was there that observations which were classified not correctly in the previous step were given more weight, and that the classifier in step M was then really trying to improve on those observations which were wrongly classified in the previous step. And that's also the idea that you saw in the visualization of this boosting algorithm that I started with, because it was there really sketched as a classification problem where it said, okay, let's look at those who are wrongly classified, let's give them more weight, let's build a classifier for that, trying to improve what we achieved in the previous step. Yeah. So the whole important takeaway from this discussion is the link between boosting and forward stage-wise additive modeling. That's the first important takeaway. And the second important takeaway is that if you look at squared error loss for regression and exponential loss for classification, then you get super intuitive boosting algorithms, because then you can say that we're going to fit base learners, weak learners, to residuals from the current model, right? Or you can say for classification, we do a weighted fit of the base learner to an output Y with certain weights, which was giving more weight to those observations wrongly classified. So that very intuitive setting, you can only give that for these two particular loss functions mentioned here, the squared error loss and the exponential loss. And as soon as you leave that framework, then you really need the idea of a gradient to replace the notion of a residual as we know it in this simple simple setting. Yeah, so that's a comment that I wanted to make with this introduction, because often you see gradient boosting, it's fitting a weak learner on the residuals from the previous step, but these residuals can only be understood as the residuals as we know them if you're working with a squared error loss. If you're working with other loss functions, these residuals will in fact be pseudo residuals, and they will be constructed by the negative gradient of our loss function evaluated in the previous step, and so on and so forth. Yeah, that's what I will explain next. Okay, so other loss functions do not give rise to such simple boosting algorithms, hence the necessity to come up with gradient boosting machines. Any questions on this, which was just meant as an introduction and might be a bit complicated, but I hope you can focus on these two takeaways: the additive thinking, so adding something to the prediction from the previous step, and then this notion of if you do squared error loss and you apply this additive thinking, you're in fact improving on the residuals. You're in fact building a model for the residuals from the previous step. And for classification, you've got an analogous interpretation there if you work with exponential loss. Any questions? Okay, anything you want to address? If that makes sense, then we're going to go further. So I described boosting techniques in general, or the boosting idea in general, as this additive thinking where we're going to improve on a certain weak learner, where we're going to boost the performance of the weak learner via this additive strategy, right? So we're going to do this with trees. And as you already know, the predictive rule in such a decision tree is if you take the features of a test observation, then you have to decide, okay, having this input features, where does my observation end up? In region Rj, let's say, then I'm going to give as the prediction, f of x is going to be gamma j, where the gamma j is typically the average of all the training observations that end up in this region Rj. Okay, so you could say that's the gamma parameter that I had in my previous notation That's a parameter that I'm estimating as part of the base learner or the weak learner that I'm using, right? So how should I see a boosted tree then? A boosted tree is the sum of trees. It's a sum of very simple trees which are constructed in a forward stage-wise procedure. So what do I need to do for each tree in each step? I need to decide on the regions constructed and those fitted values. Yeah. So I now realize that I'm making my notation a little bit complex here, but with these BJTs, I mean then the fitted values for the tree in step T and in each region that this tree is constructing. Yeah. So do note it's a sum of trees. If we compare it with random forests and with bagging, there we had an average over trees. And with bagging and random forests, those trees were grown could be grown in parallel, so they were grown independently from each other. But here it's really the sequential strategy that matters. Yeah? And we also take finally the sum of all the trees, the prediction of all the trees that we constructed. So we want to think about this. Huh? So if you do, if you're going to fit your trees in a forward stage-wise procedure, then at each step T, you're going to look for the regions and you're going to look for the fitted values of the tree in such a way that this loss function is being optimized, in the sense that you have your training observations, you picked your favorite loss function, you've got the prediction from the previous step, and now you want to add this new tree and its corresponding fitted values. And you want to do this, you want to construct this tree in such a way that the loss function is optimized. Yeah, that's what we want to do. Okay. Now with squared error loss, once again, if this L becomes my squared error loss, then again, what I'm doing here is fitting a tree to the current residuals, because with squared error loss, I'll get here the Y minus the fitted value from the previous step. So that is my residual that I have at the beginning of step T. That's the current residual. So with squared error loss, what I'm doing here is fitting a tree to the residuals from the previous step. And with other loss functions, think Poisson, think gamma, etc., we don't have this simple interpretation for our boosting algorithm, and we need to come up with something different. Okay, so how are we going to do this? So now we're really going to make the step from the squared error loss function to a more general differentiable loss function calligraphic L. And we're going to call the procedure now gradient boosting machine. So this gradient has to come in somewhere. Yeah? So what is the idea? We want to construct this boosted tree, so this additive sequence of trees. And we want to do this for any differentiable loss function, L. So we're essentially looking at the following problem. And we want to minimize this loss function. So the goal is to minimize this with respect to f, and as a constraint, we're going to say that the f that we construct should be a sum of trees, as discussed earlier on. So what are we going to do here? We're going to make the analogy with numerical optimization techniques, and we're going to say if you look at this problem from a very general point of view, so if you would look for the vector f that minimizes this loss function, yeah, if you would look in the theory on numerical optimization, then what people would do is they would use, for instance, gradient descent to look for the f hat that minimizes this given function. Yeah? So that means you're going to move in the direction where this loss function is most rapidly decreasing. So you're going to take steps in the direction opposite to the gradient. Yeah? So opposite the gradient means you're going to take the steps in the direction of the negative gradient. So the way how this is typically pictured in the literature is you're standing somewhere in the mountains and you want to get down as quickly as possible. So what are you going to do? You're going to look for where is this hill, where is the steepest path down this hill, and that's the path that I'm going to take in order to find my minimum, my valley or my cafe in the valley as quickly as possible if I would be skiing in the mountains. So that's exactly the idea. We're going to take steps in the direction opposite the gradient, or we're going to take steps in the direction of the negative gradient if we're minimizing this problem. Now, what is this strange guy over here? So I have the G for the gradient factor. And why do I multiply it with this lambda? That's the step length. Yeah, because if you are in the hills and if you go down, you find the right direction. But if you go down in very big steps, then you may end up overshooting the minimum. Or if you go down in very small steps, then it may take you a very long time to get down the hill. Yeah? So the choice of these, the size of the steps that you're going to take in this direction of the negative gradient, that's also an important choice to make. And we're going to play a bit with that in the gradient boosting machine algorithm by picking a certain learning rate or picking a certain shrinkage rate. So that's the idea of, should I take very big steps in this direction or should I take rather small steps in this direction? What would be the best strategy to find my minimum? Yeah. So this idea is then translated into the gradient tree boosting algorithm. So it starts with an optimal constant model, which would just be the root tree, so no features, no splitting being done. And what we're then going to do is we're going to fit a small tree of depth D to the so-called pseudo residuals obtained in the current model fit. Yeah. So we're going to look at these pseudo residuals, and these are defined as the negative gradient of my loss function evaluated in the current model fit. Yeah. So now, of course, the nice thing is that if your loss function is the squared error loss, and if you would calculate this derivative, then you would get minus 2 times y minus f of x, right? So if you multiply that with minus 1, you will be back with the classic notion of the residual as we know it. So with a squared error loss function, this notion of the pseudo residuals corresponds to the notion of the classic residual as we know it. But with more general loss functions, think Poisson deviance, think gamma deviance, think something else, this is the way to go. Because here then you have the appropriate notion of what this, in which direction your algorithm should move, or where your algorithm should work on improving the current fit. But we cannot call it a residual because in this classic sense, it's not a residual of the type y minus the current model fit. It's something more general, and it's inspired by this gradient descent algorithm. You see here, of course, that I can only use this, well, okay, in the basic implementation. What I need here is a differentiable loss function, because I want to be able to calculate this negative gradient. Yeah. So the way how I do this concretely will be detailed on the next sheet, but that's the idea. I construct my tree of depth D to this pseudo residuals that will give me regions. Yeah. And with these regions, I will work on improving my current model fit. And a shrinkage parameter lambda will control the learning speed by shrinking my updates. So I will not make too big steps into the direction of the negative gradient, but I will try to find a suitable learning rate or shrinkage rate in order to take these steps. And think of the analogy with the skier who wants to go down. If he goes down in very big steps, He may overshoot the cafe in the valley. If he goes down in 2 small steps, it will take him forever to reach the après-ski. So we need to find there a suitable step length or a suitable learning rate. Okay. What is then stochastic gradient boosting? That's one little extra tweak. So what are we going to do? We're going to inject additional randomness because we like that from the bagging procedure by subsampling the data at random without replacement in this case in each iteration. So we're going to work with a training sample of size delta times n, where n is the number of training data we have available, and delta is the fraction of this training data set that we want to use. Yeah? So if I put that all together, I'm achieving an algorithm that looks like this, and I'm copying here from rules paper, or from the paper that we put together. So the goal here is that you get a bit of intuition about what this thing is doing. So we initialize the algorithm by saying, yeah, we don't make any splits. We just want to fit one constant b to the whole training data set. So that's typically going to be the global average of my training data that I'm going to use as the initial prediction. That's F0. That's my initial prediction. What am I going to do then? I'm going to let the algorithm run for capital T steps. And in each step, I will randomly subsample my data. I'll create a data set of size delta times n. So delta is the fraction of the training data set that I want to use. I'll do this without replacement from the initial data set. What do I do then? For each of the observations in my subsample training data set, I'll create the negative gradient. So I create my pseudo residuals, and I'm going to fit a tree of depth d to these pseudo residuals. Now, important here is what kind of loss function will I use to do the tree construction in this particular step. That's a squared error loss, because these pseudo residuals are again classic numeric features. Numeric variables. So there is no particular loss function that I have in mind there. So typically, what I will use here is the squared error loss as the loss function to fit the tree of depth d to my pseudo residuals. That will create me certain regions called RJT here. And so they are specific for step T in the modeling process. And if I now have these regions, then I'm going to look for the B's, the fitted values in each of those regions. And those will be constructed in a bit of a peculiar way, because here I'm going to say, well, give me the B's such that if I add them to my previous step, the model fit obtained in the previous step, if I add them to that, yeah, then I'll get, then I'm minimizing my loss function that I started with. So this could be the Poisson deviance loss or the gamma deviance loss, or in a classic setting, the squared error loss. Yeah? So here you rely on the regions constructed in the previous step, but the predicted values that you will attach to each of those regions, they are determined by improving the current model fit and by adding this these constants here, the BJTs that you are looking for to this available step. Yeah. So what you're going to do here is you're going to add then the resulting tree, which is using the regions defined and the fitted constants. You're going to add them to the model fit obtained in the previous step, but you're going to do that by multiplying with this learning or this shrinkage parameter lambda. So that's the whole procedure. And in the end, what do you deliver? You deliver here the final model, which is a sum of 3 models that you constructed. So 3 models of depth d. You add them all together in a forward additive way, and that's what your GBM eventually will will deliver. Yeah. Okay. So that is the idea to do gradient boosting, stochastic gradient boosting. So once again, the stochastic comes from the fact that I do this subsampling. It's gradient boosting because I do the boosting idea. I do this forward additive sequential approach. I do it with trees of depth D in this case, and I build my trees for my pseudo residuals. And this pseudo residual is defined as the negative gradient because I want to move in the direction where this loss function can further be improved. That's the whole idea. Now, of course, there are a few tuning parameters here. In fact, there are a lot of parameters. We have the t, we have the delta, we have the small d, and we have the lambda. So these are the tuning parameters that I can play with when setting up this gradient boosting machine. So you immediately feel it's going to get complicated because there are a couple of different dimensions on which I can, on which I have to train this parameters that I'm going to use. And second comment, I have to be very careful that I'm not going to overfit. Yeah, because if I let the t become very large, then I will constantly improve. So in the end, on my training data, I will be able to achieve an error or a loss function that is going to 0. Yeah? So I should stop at the right moment. So here are my tuning parameters. This is the way how we put it up. You can find slightly different choices in the literature. As I said, there are 4 dimensions. So if you want to tune the parameters over these 4 dimensions, it's going to be really hard. It's going to take a lot of time if you do grid search and so on and so forth. So what are we going to do? We're going to tune the parameters that we see as the most essential. And we're going to fix certain values based on documentation from the literature for the other 2 parameters. Yeah. So in this case, in the paper with rule, we tuned the number of trees. That's very important. You cannot skip that one because otherwise you're going to overfit. And we're also going to tune the number d of splits in each tree. So that controls the complexity of your boosted ensemble. Because if you do d is 1, you just get a single split. D is this interaction depth. And then as the hyperparameters, we used the shrinkage parameter, lambda, and we fixed the fraction delta that specifies the size of the subsample that you will use in each iteration. So hyperparameters means I can tune these parameters, but I decided not to, and I fix meaningful values for them. So that's what we've been doing in our implementation. But once again, yeah, people can make other choices here, but keep in mind you have to keep the whole thing feasible. So really working with these 4 dimensions and setting up a tuning strategy over a 4-dimensional grid, that would take you a lot of time. Okay. Maybe a wrap up and then time for questions. So what did we do today? That's a wrap. We covered the regression tree back to the 80s, decision tree with a numeric response. That's the one that is of interest most to us. Complexity parameter decides on the size of the tree after tuning. We covered the random forest. That's beginning of the Nillies, collection of deep trees built on bootstrap data samples. We took a random selection of M-split candidates to decorrelate the trees. And we discussed the gradient boosting machines, also the beginning of the Nillies, collection of T simple trees of depth D fit sequentially and added together. Pseudo residuals were used as a response to improve the current mal fit. Yeah? And I would like to end with showing you this overview table from Rule's paper as well, because by now we should approximately be able to understand all the parameters in here. Not exactly all of them, because there are 2 that I didn't discuss so far, But this is important to keep in mind. So you see the three algorithms here, the tree, the random forest, and the GBM. So if we look at our GBM, for instance, that's the one we discussed last. What are the parameters I wish to tune? The number of trees, the tree depth. What are my hyperparameters? My learning rate, shrinkage rate, the lambda. My fraction of the training data that I will sample. And there is this kappa here, which we explain in the paper, but that has to do with a stopping criterion in the model building process of your tree. So that means you will say, I will stop splitting any further if the leaf nodes contain 1% in this case, so kappa equal to 1% of my available observations. So that's kind of a parameter which also controls the trees that you're building by putting a minimum size on the number of observations that you potentially want to have in each of the leaf nodes of your tree. So that's what the kappa is referring to. You can find more details on that in the paper. So if we then look at the parameters for the tree, we have the complexity parameter, CP, we discussed. The kappa, again, is here as a hyperparameter specified. So again, that has to do with, I'm not going to split any further if I have 1% of my training data or less in one of my leaf nodes. Then I'm going to stop the splitting of that particular leaf node. There is one tuning parameter that we didn't discuss here. That's the coefficient of variation of the gamma prior used when doing a regression tree for claim frequencies. So I'm going to discuss that next time when we're covering the implementation of the trees for Poisson data in R. But the essential thing there is what would happen if you're looking at frequency data and you build a tree, and in the tree you you would have all observations. Let me see how I explain it. All observations equal to 0. Then you would predict as the mean, the expected claim frequency for that leaf node, an exact 0. And that's something you want to avoid. Yeah, so you want to predict a number that is slightly different, and you're going to do that by using, by putting a gamma prior on the mean parameter in your Poisson in order to avoid such predictions. Yeah, so it has to do with this. And I will discuss that next time when we can really link to an R implementation of these trees and really see what's happening there with the choice of this gamma parameter. Yeah, so it's something that is super specific to the use of the regression trees in the frequency data context, but we'll come to that. And then the random forest uses the number of trees, the number of split candidates as a tuning parameters, and the hyperparameters are then the CP is equal to 0. So that means that I'm going to grow trees that are very deep. Yeah, I put the gamma here equal to 25%. So that's the same gamma used over here, but here I fix it as a hyperparameter. Kappa is the same, and the delta is again the fraction of the training data that I'm going to sample here with replacements in each step of the algorithm.